So let's talk a little bit more about isotopes. And we'll stick with carbon for now. There are isotopes of pretty much every element, but carbon is the one that we've got up here, so let's continue looking at that. Now, if we're discussing isotopes, what we're discussing is an atom that has more than the normal number of neutrons. So in the same ways that we did before, finding the number of protons, and this is again a recap from chemistry, so don't be surprised if you remember this, protons is always equal to our atomic number. That hasn't changed. The atomic number is the fingerprint, the identifying characteristic of the element. Finding the number of neutrons is the atomic mass minus the number of protons, or minus the atomic number. So this minus that. And then electrons, and this is depending on charge. And assuming it's an uncharged particle, then the electrons is always equal to the number of protons, unless that has been otherwise adjusted by becoming an ion. So if we look at our carbon, in this case, most of our carbon atoms are carbon with a mass of 12. And so there are three ways that we show this notation. And the first is to show that this would be carbon, where we put the actual mass of our current isotope as a number followed by a dash. Carbon-12 would be the standard isotope of carbon. But other isotopes exist. This one is very, very common. Now, the reason isotopes can exist is that the neutrons are simply there as, if we continue our analogy, glue. They're there to hold together the protons. So a little bit of extra glue doesn't really affect things, but a lot can make the atom unstable. So other carbon isotopes that exist is carbon-13, which has one extra carbon, and even more rare, but also possible, is carbon-14. Now, carbon-14 has a property that is not shared by the other isotopes of carbon, in that because this carbon has so many extra neutrons, if we go through the same process, this would have still a number of protons of 6, a number of electrons, if we assume that this is still stable, of 6, but a number of neutrons, because its mass is 14, less the 6 of 8. This creates what's called a radioisotope. This makes it unstable. And an unstable isotope has the potential to undergo a form of decay. Just like, well, something's a little bit tippy. We don't know when it's going to fall, but we know that it will eventually fall or break down. Unstable isotopes like this, we can't say for sure when one of these atoms is exactly going to decay or to break down or to fall apart, but we can say that at some point it will. Now this brings us to an idea that is fundamental to radioactivity. It's the concept of half-life. And no, I'm not talking about the video game, although that's probably a little bit too old for some of you, although I could be surprised. What I'm talking about here is that an unstable isotope will break down, and the degree of instability, the degree of uncertainty inside that atom is going to cause it to fall apart. And the reason is because of this excess or lack of neutrons causing the nucleus to physically break. Now we said in chemistry that you can never create or destroy elements. And that's true, but it's not entirely true. You can't create or destroy subatomic particles. But like we said in chemistry, if you hit something with a high enough beam of neutrons or a fast enough beam of protons, you can make new atoms. You can build up new particles. Or if you hit them really hard, you might actually be able to shatter atoms that currently exist. And it's easier if those atoms are already unstable. So radioisotopes, radioactive particles like this, have the potential to be broken down. much easier than their normal, stable counterparts. Now, half-life is that breakdown taking place. So the half-life is described as the length of time, oops, no, I can't spell. The length of time it takes for a sample of radioactive material to decay by 50%. We also talked about this idea of half-life when we were talking about persistent organic pollutants when we were looking at biology. The length of time it takes for the amount of that material to be removed from our environment by 50%. So the idea here is that if we start with, say, 100 atoms, that's actually a little bit of a small number for this, but let's go with 100 atoms. The half-life is the amount of time it's going to take for those 100 atoms to have 50 of those atoms, on average, decay. Now, I can't say for sure exactly which atom underwent decay. I can't say for sure exactly if this atom here on the left is going to break down or this atom in the middle is going to break down. All I know is that when you look at the entire sample, and this is more accurate the bigger your sample gets, that the time to go from 100 atoms of radioactive material to 50 atoms that have not yet broken down is a standard time that works out to what we call the half-life. So if we wait that same length of time, let's say that this was, for some unknown isotope, 5 hours. Well, after 5 hours, we have 50 atoms left. If we wait another 5 hours, we won't have lost the rest. All we will have lost is half of what was present. So we'll go from 50 to 25 atoms. And this is the fundamental difference between regular breakdown, regular decay, which happens on a set time, and this decay, which is atomic decay, which happens at a random interval, but happens when you look at a large sample over a regular time period. So this is not predictable. There is a fundamental unpredictability for each atom. If you were able to look at a single atom and say, carbon-14, when are you going to break down? You could stare at that atom for 30 seconds and it would break down. Or you could stare at that atom for 5,000 years and still keep waiting. So individually, you can't tell. But if you looked at a sample of a trillion atoms, or 100 trillion atoms, which is not that many, that's a fraction of a gram. Remember, atoms are tiny. In that sample, what you could say is that over a known time period, be it 5 hours or 5 years or 5 billion years, a portion of those atoms will decay over each time interval. We just can't say which. So half-life is a regular pattern we see in the fundamentally unpredictable breakdown of unstable ions, or pardon me, unstable isotopes. So it's unpredictable for individual atoms, but very predictable for large samples.